In the clustering problem, we are given an unlabeled dataset and we would like to have an algorithm automatically group the data into coherent subsets or into coherent clusters for us. The k-means algorithm is by far the most popular and by far the most widely used clustering algorithm. And in this video, I'd like to tell you what the k-means algorithm is and how it works. The k-means clustering algorithm is best illustrated in pictures. Let's say I want to take an unlabeled dataset like the one shown here, and I want to group the data into two clusters. If I run the k-means clustering algorithm, here's what I'm going to do. The first step is to randomly initialize 2 points called the cluster centroids. So these two crosses here, these are called the cluster centroids, and I have 2 of them because I want to group my data into 2 clusters. K-means is an iterative algorithm and it does 2 things. First is a cluster assignment step, and second is a move centroid step. So let me tell you what those things mean. The first of the 2 steps in the inner loop of k-means is this cluster assignment step. What that means is that it's going to go through each of the examples, each of these green dots shown here, and depending on whether it's closer to the red cluster centroid or the blue cluster centroid, it's going to assign each of the data points to one of the 2 cluster centroids. Specifically, what I mean by that is going to go through your data set and color each of the points either red or blue, depending on whether it's closer to the red cluster centroid or the blue cluster centroid. And I've done that in this diagram here. So that was the cluster assignment step. The other part of k-means, the inner loop of k-means, is the move centroid step. And what we're going to do is we're going to take the 2 cluster centroids, that is the red cross and the blue cross, and we're going to move them to the average of the points colored the same color. So what I'm going to do is look at all the red points and compute the average, that's really the mean of the location of all the red points, and we're going to move the red cluster centroid there. And the same thing for the blue cluster centroid. Look at all the blue dots and compute their mean, and then move the blue cluster centroid there. So let me do that now. I'm going to move the cluster centroids as follows, and I've now moved them to their new means. Right? So the red one moved like that, and the blue one moved like that, and the red one moved like that. And then we go back to another cluster assignment step. So we're again going to look at all of my unlabeled examples, and depending on whether it's closer to the red or the blue cluster centroid, I'm going to color them either red or blue. So I'm going to assign each point to one of the 2 cluster centroids. So let me do that now. And so the colors of some of the points just changed. And then I'm going to do another move centroid step. So I'm going to compute the average of all the blue points, compute the average of all the red points, and move my cluster centroids like this. And so let's do that again. Let me do one more cluster assignment step. So color each point red or blue based on what it's closer to, and then do another move centroid step. And we're done. And in fact, if you keep running additional iterations of k-means from here, the k-means, the cluster centroids will not change any further, and the colors of the points will not change any further. And so, this is the at this point, k-means has converged, and it's done a pretty good job finding the 2 clusters in this data. Let's write out the k-means algorithm more formally. The k-means algorithm takes 2 inputs. One is a parameter k, which is the number of clusters you want to find in the data. I'll later say how we might go about trying to choose k, but for now, let's just say that we've decided we want a certain number of clusters, and we're going to tell the algorithm how many clusters we think there are on the data set. And then k-means also takes as input this sort of unlabeled training set of just the x's, and because this is unsupervised learning, we don't have the labels y anymore. And for unsupervised learning, or for k-means, I'm going to use the convention that xi is an Rn dimensional vector. And that's why my training examples are now n dimensional rather than n plus 1 dimensional vectors. This is what the k-means algorithm does. The first step is that it randomly initializes k cluster centroids, which I'm going to call mu1, mu2, up to mu k. And so in the early diagram, the cluster centroids corresponded to the location of the red cross and the location of the blue cross. So there we had 2 cluster centroids, so maybe the red cross was mu1 and the blue cross was mu2, and more generally we would have k cluster centroids rather than just 2. Then the inner loop of k-means does the following. We're going to repeatedly do the following. first, for each of my training examples, I'm going to set this variable ci to be the index 1 through k of the cluster centroid closest to xi. So this was my cluster assignment step, where we took each of my examples and colored it either red or blue depending on which cluster centroid it was closest to. Okay, so ci is going to be a number from 1 to k that tells us, is it closer to the red cross or is it closer to the blue cross? And another way of writing this is I'm going to, to compute ci, I'm going to take my ith example xi, and I'm going to measure its distance to each of my cluster centroids. This is mu and then a lowercase k, right? So capital K is the total number of centroids, and I'm going to use lowercase k here to index into the different centroids. But so ci is I'm going to sort of minimize over my values of k and find the value of k that minimizes this distance between xi and the cluster centroid, and then the value that minimizes the value of k that minimizes this, that's what gets set in ci. So here's another way of writing out what ci is. If I write the norm between xi minus mu k, then this is the distance between my ith training example xi and the cluster centroid mu subscript k. This here, that's a lowercase k. So uppercase k is going to be used to denote the total number of cluster centroids, and this lowercase k, lowercase k is a number between 1 and capital K. I'm just using lowercase k to index into my different cluster centroids. That's this lowercase k. So that's the distance between the example and the cluster centroid, and so what I'm going to do is find the value of k, of lowercase k, that minimizes this, and so the value of k that minimizes this, that's what I'm going to set as ci. And by convention, here I've written the distance between xi and the cluster centroid. By convention, people actually tend to write this as the squared distance. So we think of ci as picking the cluster centroid with the smallest squared distance to my training example xi. But of course, minimizing squared distance and minimizing the distance, that should give you the same value of ci. But we usually put in the square there just as a convention that people use for k-means. So that was the cluster assignment step. The other inner loop of k-means does the move centroid step, and what that does is for each of my cluster centroids, so for lowercase k equals 1 through k, it sets mu k equals to the average of the points assigned to cluster. So as a concrete example, let's say that one of my cluster centroids, let's say cluster centroid 2, has training examples 1, 5, 6, and 10 assigned to it. And what this means is this means that C1 equals to C5 equals to C6 equals to, and similarly, C10 equals to, right? If we got that from the cluster assignment step, then that means that examples 1, 5, 6, and 10 were assigned to cluster centroid 2. Then in this move centroid step, what I'm going to do is just compute the average of these four things. So I'm going to x1 plus x5 plus x6 plus x10, and then I'm going to average them. So here I have 4 points assigned to this cluster centroid, so I'm just take 1/4 of that, and now mu2 is going to be an n-dimensional vector, because each of these examples, x1, x5, x6, x10, each of them were an n-dimensional vector. And when I add up these things and divide by 4, because I have 4 points assigned to the cluster centroid, I end up with my move centroid step for my cluster centroid mu2, and this has the effect of moving mu2 to be the average of those 4 points listed here. One thing that I've sometimes been asked is, well, here we said let's let mu k be the average of the points assigned to that cluster, but what if there's a cluster, what if there's a cluster centroid with no points, with 0 points assigned to it? In that case, the more common thing to do is to just eliminate that cluster centroid, and if you do that, you end up with k-1 clusters instead of k clusters. But sometimes if you really need k clusters, then the other thing you can do if you have a cluster centroid with no points assigned to it is you can just randomly reinitialize that cluster centroid. But it's more common to just eliminate a cluster if somewhere during k-means it ends up with no points assigned to that cluster centroid. And that can happen, although in practice it happens not that often. So that's the k-means algorithm. Before wrapping up this video, I just want to tell you about one other common application of k-means, and that's to the problems with non-well separated clusters. Here's what I mean. So far we've been picturing k-means and applying it to data sets like that shown here, where we have three pretty well separated clusters, and we'd like an algorithm to find maybe the three clusters for us. But it turns out that very often k-means is also applied to data sets that look like this, where there may not be several very well separated clusters. Here's an example application to t-shirt sizing. So let's say you're a t-shirt manufacturer, and what you've done is you've gone to the population that you want to sell t-shirts to, and you've collected a number of examples of the height and weight of these people in your population. So and I guess height and weight tend to be positively correlated, and so maybe you end up with a data set like this, with a sample, with a set of examples of different people's heights and weight. Let's say you want to size your t-shirts. Let's say I want to design and sell t-shirts of three sizes: small, medium, and large. So how big should I make my small, and how big should I make my medium, and how big should I make my large t-shirts? One way to do this would be to run the k-means clustering algorithm on this data set that I have shown on the right. And maybe what k-means will do is group all of these points into one cluster, and group all of these points into a second cluster, and group all of those points into a third cluster. So even though the data, beforehand it didn't seem like we have three well-separated clusters, k-means will kind of separate separate out the data into multiple clusters for you. And what you can do is then look at this first population of people and look at them and look at the height and weight and try to design a small t-shirt so that it kind of fits this first population of people well, and then design a medium t-shirt and design a large t-shirt. And this is in fact kind of an example of market segmentation, where you're using k-means to separate your market into three different segments, so you can design a product separately, that is the small, medium, and large t-shirts, that tries to suit the needs of each of your three separate subpopulations well. So that's the k-means algorithm, and by now you should know how to implement the k-means algorithm and kind of get it to work for some problems. But in the next few videos, what I want to do is really get more deeply into the nuts and bolts of k-means and talk a bit about how to actually get this to work really well.